Josh Ruderman. Josh finished his PhD in Princeton in 2011. He then spent 3 years in Berkeley as a Miller Fellow and has joined the faculty at NYU at the Center for Cosmology and Particle Physics in 2014. Josh is broadly interested in particle theory with a focus on physics beyond the standard model. His work often resides at the interface of theory and experiment, the latter including high-energy colliders, direct detection experiments, and astrophysical measurements. And today he's going to tell us about unknown knowns at the LHC and New York.
Thanks very much for the intro. So yeah, I know some of the group here well. This is my first time here at Technion. It's great to be here. I'll be around through Wednesday if anyone wants to chat. This talk will be about the Large Hadron Collider, LHC, and I'll give you my take as a theorist on both the status, but mainly about what we can learn in the future as this experiment continues to run. The title is a clue that the talk will involve things we know and things we don't know. Okay, so first, just to know, remind you where it's situated. The LHC is in a tunnel underground. It's 27 kilometers circumference. It's located at the Swiss-French border near Geneva. I'm actually on leave at CERN this semester, so you can see my apartment over there. Okay, so we accelerate protons in this tunnel. Each of these protons has an energy of 6,500 giga-electron volts. And the protons are brought to collide at special interaction points located inside detectors that measure the outputs of these collisions. So we collide the protons. When we collide the protons at these energies, they are completely destroyed. And then we make new particles. So we literally do alchemy. The energy from the protons is converted into new particles. We know exactly what goes in, two protons with energy 6,500 GeV each. We don't a priori know what will come out. It's random because of quantum mechanics, and also the energy allows us to assess whatever particles are present. And in this way, it's really a discovery machine in the sense that it will tell us what particles exist. Okay. Why do we do this? Well, really the goal, of course, is to zoom in. So by going to higher energy, as the same as going to smaller length scales, these are equivalent by the uncertainty principle. So just for fun, one slide with all scales. Observable universe, galaxies, stars, people, bacteria, atoms. The LHC is studying length scales of 10 to the minus 20 meters. So that's what we're trying to understand now. So the left of that is really question marks. We know there are other things. There needs to be physics that explains quantum gravity, like perhaps string theory. There's physics that explains stellar expansion, near universe inflation. But really, it's question marks. And we're trying to kind of get at those by going to smaller scales. So that's the big picture goal. Just some numbers to have in mind. For a characterization, I already mentioned the energy of the protons, 6,500 GeV or 6.5 TeV, tera-electron volt per proton. That's 6,900 times the mass of the proton. So the protons are highly relativistic, with energy much bigger than their mass. The center of mass of these collisions is twice the proton energy in the lab frame, so that's 13 TeV. That's the total energy budget available for making new particles. When the LHC was originally conceived, we were hoping to get to 14, but they decided it's safer to run at 13, and maybe it'll crank up a little, or maybe it'll just stay at 13. Okay, so the collisions occur inside large detectors that you can think of morally as cameras. And since this is a theory talk, I'm not going to tell you how these work. You can ask your experimental colleagues. There are Atlas people here. But you can see it's the size of a building. Those are people. It has 4 pi coverage, and basically it measures what particles come out of the collisions, it measures their energy, and it measures their momentum. You have magnetic fields that bend charged particles that we can use to infer their momentum, and so on. So you can tell if photons are produced, electrons, muons, protons, you can tell their energy and momentum. That's all I really need to know for this talk. Okay? We collide protons. We measure the number of protons we've collided using a unit called inverse femtobarn, which is a measure of the luminosity. For each inverse femtobarn, that corresponds to about 10 to the 14 distinct proton collisions. Another way to measure it would be that we make 40,000 Higgs bosons per inverse femtobarn. Okay, and then this shows how many of these inverse femtobarns we've collected so far. This is the current status for the Atlas detector. The other big detector CMS is similar. This is here versus inverse femtobarns. You see the total that are good for physics collected by the end of 2017 is 80 inverse femtobarns. So then that 10 to the 14 protons times 80 would be the total number of collisions. You see most of that, well, half of that was actually last year, 2017. So that was the best year so far. The other big year was 2016. There was a smaller amount in 2015. If you go further to the left, then it was running actually at a lower energy. It was running at 7 or 8 TeV center of mass before 2015. So this shows the full data set at 13 so far. It just started running for 2018, so I think last week were the first collisions with stable beams, not yet collecting physics, but imminently we'll start 2018, and the goal this year is to even do more than that. Okay, so that's where we are so far. What have we achieved so far with this? Well, you all know, of course, the big headline discovery from the LHC. We discovered the Higgs boson, the first fundamental spin zero particle to be discovered. It was discovered in 2012 using the lower energy collisions before we ramped up to 13 TeV. Led to the Nobel Prize for theorists in 2013. We now precisely know its mass. So its mass is 125 GeV. We know this to better than 1% precision. It has about the mass of, say, a xenon nucleus. Now that we've discovered the Higgs, a major goal moving forward is to study its properties, and in particular to study its interaction strength to other particles. The Higgs gives mass to particles, and we predict that it couples to particles proportionally to their masses. So this line shows, so here we infer its coupling to other particles based on the probability the Higgs decays to various particles. We predict a line saying that it couples proportionally to mass. And so far, the data are consistent with that and have achieved the precision of about 10% in the best measured cases for measuring the size of these interactions. So at least at the sort of 10% precision, it does couple to mass as was theoretically predicted. Okay? And now that we have the Higgs, that completes what we call the standard model of particle physics. This is our current understanding of particle physics, first proposed by theorists in the 1960s. And it encapsulates all known particles and all known interactions that we've seen in experiments. So we have the Higgs that we were just talking about, spin 0. There are spin 1 particles that communicate forces that I'll talk more about later. Okay, there's leptons, which includes the electron and its heavier cousins, the muon, the tau, neutrinos, very weakly interacting. Quarks. The lightest two quarks are what make up protons and neutrons. So proton and neutron is determined based on the composition of these quarks. These heavier quarks are not present in ordinary matter because they rapidly decay. And that's everything. And well, at the LHC, we've been studying all of these particles in detail. So we make all of them. We study the rates of making them. So this slide is a lot of information, but this is a compilation of studies of standard model processes by the ATLAS experiment so far at the LHC. And the different columns here correspond to production of different particles from the standard model. So, well, for example, photons would be this column, Higgs is, or over here. Sorry, over here. Okay, and the y-axis is the cross-section for producing these, which is just telling you the probability in a given proton collision that you make certain particles. And you determine this by counting the number of events of each of these types. And you can see that there's many different types of particles in the standard model that we're making, and it spans many different cross-sections. This is a lot of scale. And just what you take away from this is across this large ensemble of measurements, these measurements agree with the predictions of the standard model. The white dots show experimental measurements. The gray bands, okay, they're a little hard to see, they show the theoretical predictions, and they agree with each other across this entire ensemble. So that this is that we can do this is an amazing achievement, both experimentally but also theoretically. There's been great advances in making predictions with the standard model to check against these experimental measurements. So bottom line, so far, the LHC tells us that the standard model describes what we're seeing at this TeV energy scale. Okay? But it's not the end of the game, it's actually only really the beginning in terms of the LHC's full program, which is summarized in this slide. This is the amount of proton collisions we anticipate to collect in the next few years. So this is us now, 2018. This is by year. The y-axis is that luminosity we were talking about in Rumsfeld. The kind of core phase of the LHC is going to end by the end of 2022. And by then we're going to have about 300 Rumsfeld. The number was 80 now. And then the LHC is going to be upgraded into what we call high luminosity LHC phase, which is going to begin in 2025. And during this phase, it's going to collect 10 or more times the data that will be collected in the initial phase that we're in right now. And it's going to end actually in the sort of mid-2030s. And by then, we'll have, well, we now only have 3% of the total number of proton collisions that we anticipate collecting by the mid-2030s. So it's actually early days in terms of the number of proton collisions. Okay, but we're even thinking beyond this because it takes a lot of money and a long time to design and build these experiments. So we don't want to just wait till then to decide what to do. We're thinking now what to do next. And so there are a number of different proposals for what could be next. I'll just highlight two that are receiving a lot of attention. One idea for what's next would be to build an Electron-Positron collider. It would have a center of mass of 240 GeV, and the reason for choosing this number is that's the energy where you would maximize the number of Higgs bosons you produce, and the goal of this machine would be to precisely study the Higgs properties in a cleaner environment than we have at the LHC. So as you discover the Higgs, an E+ E- collider could then be the machine to study it precisely. And another kind of next step that's considered would be an even higher energy proton-proton collider. So the LHC is 13 TeV, and people are envisioning going even up to as high as 100 TeV with the next collider. And actually, steps 1 and 2 you could do in the same tunnel. So you could dig a new circular tunnel first, do the +E- phase, then do a proton-proton phase. So that both of these options are being actively studied at CERN. At CERN, they call this the FCC, for Future Circular Collider. If it actually is built, we'll probably have to change the name. It would be a bigger tunnel. That's the 27-kilometer LHC. This is the tunnel size we're looking at now. There's already civil engineering studies that have been done for this. Actually, a few weeks ago, I was at a conference, and they have a yearly conference of people studying this. There were 500 people, mostly engineers and accelerator physicists. And the studies are getting quite realistic. I met people giving talks on safety of the machine, that they're engineering, how to deal with helium leaks in the tunnel. Like, it's really into the details. There's a competing effort in China. There's less people. It's a smaller community there, but growing. And the kind of budget within China for this type of physics is growing and has a lot of potential. This is a slide from a conference in Hong Kong in January that I was at, where they're also considering similar two options. There's 6 different sites where they're doing civil engineering studies in China. If you do it in Europe, you're probably going to do it at CERN, but in China, you could do it wherever. So they're considering a bunch of places, talking to local governments. Well, in principle, either of these, or both of these, or one of these could happen, but this is just giving an idea of things that could happen in the future. Okay, what's the time scale? We'll stay healthy. Okay, so this shows a slide from this conference I mentioned in Amsterdam, studying FCC at CERN. So these are a potential schedule for what you could do at CERN. Okay, that's a lot of information, but this is magnet development. Yes, these are here. This is magnet development. This is the 100 TeV proton collider. This is the new E+ E- collider. This is a different idea where you keep the LHC tunnel but increase the energy of the magnets. The key thing to look at here is this yellow box. Earliest that these would start is around 2040. I will not be retired yet. Okay. So that's kind of the immediate game and also the long game. I think it's good to have the experimental trajectory in mind. But really, for the rest of the talk, I want to talk about theory. I want to talk about what we can learn from the rest of the LHC that will certainly happen, and then these more long-term ideas that might happen. Since I'm at CERN this semester, I got to go underground, so I flash these selfies. I can't even keep my eyes open for selfies. Okay. Okay. So what physics can we learn? And to answer this question, well, I'm American, so I of course want to take guidance from a particular Donald, as I should. And actually, I know that this guy is actually much more popular in this country than in my country. But sorry to disappoint you, but it is not who I want to talk about. And also not this one. I want to talk about a Donald from a decade ago, Donald Rumsfeld. He was the US Secretary of Defense actually twice. But I'll focus on this period. He was Secretary of Defense during the lead up and then during the US second invasion of Iraq. So he helped motivate it and implement it. And I want to read you something he said in 2002. This is a bit famous, you may have heard this. This was at a press conference before the Iraq War, but during the lead up. He was asked by a reporter to comment on the seeming lack of evidence showing that the Iraqi government was trying to provide weapons of mass destruction to terrorists. Now, any good politician, if they're asked a question that they don't want to answer, they answer a different question. You'll see I'll do that if you ask me questions. So instead of answering this question he provided a general classification scheme of knowledge. So let me read you what he said. He said, as we know, there are known knowns. There are things we know we know. We also know there are known unknowns. That is to say, we know there are some things we do not know. But there are also unknown unknowns. The ones we don't know, we don't know. So the time people kind of made fun of him for talking in a funny way, but actually this is a pretty smart classification scheme of knowledge. He had in mind military intelligence, but I think it's more generally useful. So I want to really think about this, so let's break it down into what I'll call the Rumsfeld matrix of knowledge. So these are the three types of knowledge that he identified. And this way organized, it makes it clear that he forgot, he left out a type of knowledge. He's a smart guy though, and he realized that, so he left out unknown knowns. So a few years later, he wrote a memo where he provided a definition for unknown knowns. This one's a little more subtle. And he says, okay, there are also unknown knowns, things you think you know, that it turns out you do not. Okay? So now that
can also be something that you don't know that you know, but you really know it.
you just wait. Oh, sorry. This is a very smart question. But for now, let's take this into original definition. Okay. So now we have the full matrix of knowledge that Rumsfeld provided. This can be applied to anything, not just military intelligence. So for this talk, I'm going to apply this to particle physics. Okay, so known knowns are, of course, the standard model. So we know the standard model theoretically. We know how it's defined. We can use it to calculate and make predictions for what you'll see at the LHC as we go forward. Okay, known unknowns. Well, there are cases that we know the standard model is inadequate. Things that it cannot describe, where we know there's more physics. It does not describe dark matter, does not describe quantum gravity. These are, we don't know what describes those, so that's why it's a known unknown, but we can look for these things at the LHC. Okay, well, unknown unknowns, well, I guess I could just leave a question mark. But yeah, this would be kind of surprises. And as I told you, we know what we're putting in, 2 protons of well-defined energy. We don't know a priori what's going to come out. So that means that surprises can happen. Okay, unknown knowns is more subtle. That's why he forgot it at first. For this talk, what I'll have in mind is the case where there is new physics. The new physics cannot be produced directly, perhaps it's too heavy. It can still leave imprints on physics we're measuring that are more subtle to uncover. I think that's kind of the most interesting case, which is why I made the title of this talk. Okay, so my plan for the remainder of the talk is going to be to move clockwise through the Rumsfeld matrix and then show some examples of each type of knowledge that we can attack with the LHC and beyond. Okay, so that's the plan. Okay, so first, known knowns, things we know. In this case, the standard model that I already mentioned, that we completed with the discovery of the Higgs boson. We know its description theoretically, but we can still test it at the LHC, and in particular, we can test it in qualitatively new regimes by accessing higher energies than we had before, and also now we have this new Higgs boson. So for example, one major goal moving forward is to continue to study the properties of the Higgs with as much precision as possible, it being the first fundamental spin-zero particle and related to mass generation. It really has a special place in the standard model. So this slide shows you the ultimate estimates of the ultimate sensitivity that we can check various Higgs interactions at the LHC and this FCC next step that I mentioned. So here for the LHC, this is the ultimate precision after the full 100%, where we're only 3%, so by the 2030s. And this shows, so these are different, the Higgs coupling to different states, and then this is the fractional precision that you can measure the size of the interaction on a log scale. And so if you look at the light blue for the LHC, it varies by channel, but roughly it's around 10% precision is about the best you can do. And we're already getting close to that. We can prove it by an order 1 factor. However, if you look at these next steps, especially this FCCE, which is this electron-positron collider at 240 GeV, you can get to percent level and even sub-percent level understanding of the couplings. So you can go beyond the sort of crude 10% of the LHC to really precision Higgs physics. But it is still a known because the standard model makes a well-defined prediction for each of these couplings that we can then check. Okay? So I'll talk about a slightly more non-trivial case involving how we can check the property of forces at the LHC. Before I get to the punchline, let me just step back and make some general statements. Okay, so in the standard model, there are 3 types of forces. Electromagnetism, you all know. Also weak and strong nuclear forces. So weak nuclear force gives something to radioactive decay. Strong nuclear force binds nuclei together. And in general, in particle physics, there's a precise correspondence between forces and particles that mediate forces. Each of these forces is mediated by one or more spin-1 particles. So the photon for electromagnetism, the nuclear force, it's the W and the Z. These are massive spin-1 particles. The Z is electrically neutral. The W plus or minus has electric charge. Why it's plus or minus. And for the strong nuclear force, the gluon mediates it. So for each force, there's a mediator. Okay. And the strength of each of these forces is determined by a different coupling constant. For electromagnetism, it's the fine structure constant, alpha. There's an analogous alpha for these other two forces. Okay? And a key prediction in general particle physics, and also in the Standard Model specifically, is that the strength of forces is not actually constant. It varies with energy. The colloquial way we describe this is we say that the forces, the couplings run, but we just mean that they depend on energy. This plot shows the prediction within the Standard Model of how the strength of the forces depends on energy. So here's energy across many, many decades. So this is 1 over the strength of the forces. The reason for the 1 over is you get nice straight lines. So weaker is higher, stronger is lower. There's a technical fact that electromagnetism at high energies becomes something called hypercharge, but you can think of it as a high energy electromagnetism. The important thing is that the two nuclear forces get weaker, are predicted to get weaker as you go to higher energies, whereas this electromagnetic force gets stronger as you go to high energies. At the low energies, around 100 GeV, they're all quite different. They actually become comparable. At higher energies, the fact that this observation they become comparable is what led to the idea of what's called grand unified theories, that maybe there's one force here that they all originate from. Yeah.
Can you say what the hypercharged force is?
Yeah, it's electromagnetism. Basically, there's a technical difference that makes us change its name.
What's the difference? It changes the name.
Yeah, so the photon at low energies is not the photon at high energies. The photon at low energies is a mixture of the photon from hypercharge and one of the force carriers of the weak nuclear force. So there's sort of a mixing at low energies between the force carriers. So what we see as electromagnetism is really a mixture of a piece of this one and a piece of this one. But otherwise, mathematically, it behaves exactly like a high energy electromagnetism. So there's a technical difference we're not going to worry about. Okay. So, yeah, we predict they change with energy. The LHC is doing measurements up to the purple line, and they have changed in energy from, say, 100 GeV to the purple line, and that's something we can look for. This is a kind of non-trivial prediction of the Standard Model that we would like to test. And this has been tested for the strong force by a bunch of experiments across a wide range of energies, and really confirmed the prediction of the Standard Model that it gets weaker with energy. So what this plot shows us is the strength of the strong force versus energy, and we've seen it change in strength by about a factor of 2 across the range of energies that experiments have measured the properties of the strong force. These highest energy constraints come from the Large Hadron Collider, which is the only way we assess its behavior at these energies. As you go to lower energies, other experiments are relevant. So that's good. But actually, this check has not yet been performed for the other two forces. So actually, right now, there's no experimental statement about the energy dependence of the hypercharge or weak nuclear forces at energies above around 100 GeV. That's still an open question experimentally. We would like to check, do they depend on energy similarly and match the Standard Model prediction. It is still a known because the Standard Model makes a very well-defined prediction of how these forces.
Why there is systematic deviation with low energies?
Oh, you're worried? That's all one sigma. You're worried about these being high?
Just ask.
Yeah, no, that's a good question. This is H1. I am not an expert on that.
It's systematic.
But yeah, indeed, yeah, exactly. Systematically, you say. So typically for these measurements, there's a lot of correlation.
It should be more accurate at low energy, no? It should be more accurate at low energy. You have more luminosity.
Well, they're all consistent with. Oh, you're asking why are the error bars bigger?
Yeah.
Well, so indeed at low energy, the theoretical understanding gets worse because you have larger corrections when the force is stronger, which could be part of it. And also, the physics actually gets cleaner at high energies. Sort of at high energies, you can think about it in terms of quarks. And gluons at low energies, it becomes hadrons and it gets much messier, both experimentally and theoretically. So it's probably why the error bars are smaller. Okay, but anyway, it's actually a very good agreement across the whole range. Okay. So, what I want to focus on is the other two forces whose energy dependence hasn't been measured. I think that they can be. We can do it at the LHC and much better beyond the LHC. The way I think we can do this is what we call Dilepton production. So in proton collisions, like at the LHC, we have events where we produce a lepton and an anti-lepton, like an electron and a positron, or a muon and an anti-muon. So this shows the process where we produce a lepton and anti-lepton. What we do is we take a quark from one proton and anti-quark from the other proton. Protons have some amount of anti-quark in them. Those are destroyed, and then through the force carriers, you produce a lepton and an anti-lepton. This shows an example event at the LHC where this is one of the highest invariant mass events with muons, about 2 TeV. And sorry, so invariant mass is a kinematic variable that we can use to characterize this event. It's a function of the energy of the lepton and anti-lepton and their momenta. And the reason it's a useful variable is it's Lorentz invariant, and it is a characterization of the total energy. So kind of a harder energy dilepton event will have a larger value for this invariant mass. This is one of the highest energy dilepton events. And having a variable that measures the energy is very important if you want to measure how the forces depend on energy. And in particular, yes, this shows an example of measurements of the dileptons. This is from CMS. So this shows the cross-section, which is just the probability of making dileptons with these different invariant masses. You see it's falling, so you're much more likely to have lower energy events than higher energy events. You get a bump over here. This is where you're producing this Z boson particle that mediates one of these force mediators. But the reason that I'm interested in this is that this secretly probes the energy dependence of these forces, because this cross-section as a function of invariant mass actually depends on the strength of the force at the invariant mass of a given event. So because of this relation, the shape of this part of the invariant mass spectrum can be interpreted as being sensitive to the energy dependence of the weak forces. So although presently there's no experimental statement about their energy dependence above 100 GeV, actually properly interpreted, this measurement is actually making a statement about that. And then you could ask, well, can you measure the size of the effect that's predicted in the standard model? So we looked at that, and the answer is right now it's very hard. With the full LHC data set, it's borderline, and then with a higher energy collider, you can measure it very easily. So with the full LHC data set, by the 2030s, we estimated that you can confirm that the weak nuclear force gets weaker with energy as predicted in the standard model at about the 2 to 3 sigma level. And I'm giving a range there because it ultimately depends a bit on experimental systematics where we have to make a projection. If you had a 100 TeV collider, because you're going to higher energies where the effect is bigger, the force has gotten weaker by a larger fractional amount, you can decisively tell that it's getting weaker by easily the 5 sigma level. So this is an example, again, of a known because theoretically we have a concrete prediction to compare to, but it's still a qualitative effect of the standard model that is exhibited at high energies, hasn't been tested yet, that we can begin to test at LHC and test better as we go to higher energy. Okay? So those are two examples of known knowns. Next, known unknowns. So we know there are some things we do not know, and there are a number of deficiencies in the standard model, things the standard model doesn't explain that we would like to understand. So here I summarize some of them. Why is there more matter than antimatter? Physics of quantum gravity, inflation, dark matter. Here I put solid lines for the ones where we're more confident that we need new dynamical physics, and I put dashed lines for puzzles that are more theoretical, and they're what we call fine-tuning problems. They're values of parameters we don't understand that we think point to new dynamics. Personally, I'd say we're more confident for the solid ones than the dashed ones. Each of these could easily be a 1-hour talk, and many of these can be tested by more data at the LHC. So I'll just make a personal choice and choose one of them, dark matter. I'll talk about this a little more, about how we can learn about it at the LHC and in other ways. But yeah, it's something that we know that we don't know, because we don't know what it is, but we know it's there. Okay, so you've probably seen this. This shows the cosmic energy budget We now have percent level understanding of it. The energy of our universe is mostly dark energy, is driving accelerated expansion, but among the matter, it's mostly dark matter and only about 5% known matter. How do we arrive at this pie chart? Well, mainly we arrive at this precise understanding from studying the cosmic microwave background. This is the black body radiation left over from when the first atoms formed. It now has a temperature of a few Kelvin. You can take this radiation, form its power spectrum. So this shows the measurement by the Planck satellite. This video shows how the shape would change if you vary the amount of dark matter. So this is really how we get this precise number. It is from this shape change. And in particular, if you watch the video carefully, if you look at the relative heights of the first and third peaks, they're very sensitive as the amount of dark matter is varied, and then but this precise measurement allows for that precise number. So that's how we know that. Yeah, we like to talk about rotation curves, bullet cluster, but this is how we really know precisely the amount of this stuff. Okay, now we want to understand what is it made of, what is its particle nature, and if it's made of particles, those particles must have a few properties. They must be stable on cosmological timescales because they were made in the early universe and are around now. They must be electrically neutral because they're dark. They must have been non-relativistic when galaxies formed. And there's no particle in the standard model as a single particle that satisfies these three properties. So I showed you before, all the standard model particles, you can cross off all of them if you use these three. So that seems to require, therefore, new particle physics beyond the standard model. But we don't know what it is, so it's a good example of a known unknown. As a particle physicist, we want to figure out what it is. So one idea for what it could be comes from an idea called supersymmetry. Supersymmetry posits a new symmetry that relates particles of different spin. It relates bosons and fermions, and it predicts a new particle for each of the standard model particles with different spin. So the photon Z and the Higgs boson, these are all bosons. And supersymmetry predicts that they're corresponding fermions. That we call them neutralinos because they're electrically neutral. So supersymmetry predicts new electrically neutral fermions that haven't been observed in experiment, but are predicted to exist if the symmetry operates in nature. The lightest of these new superpartner particles is can be stable on cosmological timescales, as dark matter need be. And in detail, if you look at the cosmology, you end up with roughly the right amount, or can get the right amount. So the lightest of these neutralinos is a good candidate for dark matter. It's an example of a broader idea we call a weakly interacting massive particle WIMP. And this observation that supersymmetry can be connected to the dark matter dates back to the early 80s. So it's been one of the big drivers, both of supersymmetry and dark matter. So we want to test this idea. Is this idea right? Okay, before I get to LHC, let me talk about another way we can test this, or the primary way that we often look for dark matter is with the technology we call direct detection. We look for dark matter coming in, scattering against nice clean experiments. So dark matter comes in, leaves some energy, and then if you don't see large amounts of energy being left, you can exclude there being dark matter. So this shows the present status of this experimental program. Here, the x-axis is the dark matter mass, the mass of the dark matter particle, log scale. The y-axis is the size of the cross-section of dark matter scatter against nuclei. So that determines the probability that the dark matter will scatter a nuclei. The shaded area is excluded by present experiments, and the way I made this is that each color shows which experiment sets the strongest limit as a function of that mass range. So the shaded area is excluded. The white area is still allowed. And you could ask how far down can these experiments go? Well, unfortunately, there's a limitation. In the red region, there's a background from neutrinos. These neutrinos from the sun or the atmosphere that scatter coherently, elastically against the nuclei in these detectors. And in the red region, you would have more events from neutrinos than from dark matter, which make it hard to find dark matter. So if we're going to find dark matter with this type of experiment, we hope it lives in the white region. Because it cannot live in the upper region, and we're kind of screwed if it lives in the red region. And well, this shows various experiments, most of which can happen over the decadal timescale, that are going to, in fact, cover most of this white area. So either we'll see it, or if we don't see it, then it's probably in the red region. Okay. This is sort of a general way of parameterizing it in terms of the experimentally relevant quantities mass cross-section. But now you can ask, how does this image map into this supersymmetry idea. Well, in supersymmetry, the way you generate this scattering of dark matter against nuclei is by exchanging the Higgs boson, if dark matter couples to the Higgs boson. So if dark matter has some coupling to the Higgs, then you can exchange the Higgs and scatter it against nuclei. So, and now that we know from the LHC that Higgs exists, this is a very motivated way to look for dark matter. And this coupling is predicted to be present in supersymmetry. This shows how the size of the cross-section depends on this unknown coupling. And physically, what this coupling size is measuring is the fraction of the dark matter mass that is coming from the Higgs. So the dark matter may have some mass from the Higgs, some mass from other sources, but the mass it gets from the Higgs determines the size of its cross-section scattered against nuclei. Now if we go back to this direct detection plot, we can draw these purple lines that show the strength of the dark matter's coupling to the Higgs, and couplings of this size are what is predicted in supersymmetry. So this region that's still allowed that we're going to test with the next round of experiments is theoretically very motivated and interesting for supersymmetry. So that's all well and good. What does this have to do with the LHC? Well, the problem is that supersymmetry doesn't, unfortunately, make a definite prediction for the size of this coupling Y. This is something that myself and a few others looked at in detail a few years ago, and we found that there are special points within the parameters of supersymmetry, depending on the masses of superpartners, where this coupling vanishes exactly. So not only does supersymmetry not make a prediction for the size of this coupling, but it can be zero. So we were the first to kind of classify these unfortunate places where the coupling is zero. We call them blind spots. So they literally go down to zero, and then you will not see those choices of parameters with these direct detection experiments. So while the next round of progress will be interesting, there's a limitation here that the coupling to the Higgs can be too small, such that you fall into the region where the neutrino background is bigger than the dark matter rate. And well, this is where the LHC or colliders come in. They provide a really independent way of looking for supersymmetry that differs from direct detection, because direct detection is really just looking for this coupling, but the LHC can look for other couplings. So for example, the dark matter can couple to the W boson and can be produced if you plot an up quark from one proton, anti-down quark from the other proton, and you can make these neutralinos at the LHC. So this is a study recently that was motivated by our identification of these direct detection blind spots, and they looked at the LHC's ability to look for them, and they found that the LHC has a pretty broad ability still to discover dark matter by producing it using couplings that don't involve this Higgs boson coupling that the direct detection is seeing. So this entire plot lives within these blind spot, direct detection blind spot parameters that we identified, and then they show that there's 5 sigma discovery reach out to over here. So here the y-axis is the mass of the dark matter, the x-axis is the mass of the superpartner of the Higgs boson that's related to the rate for this process. But the takeaway, what you take away from this is just that the LHC provides a complementary way of looking for dark matter than direct detection, because it tests different couplings that the direct detection experiments are not sensitive to. And because, unfortunately, supersymmetry doesn't make a concrete prediction for the size of the cross-section in direct detection, in fact, it can be zero, and in those cases, it really could be the LHC that's needed to produce it. Okay, so that was the one example I wanted to give you of a known unknown, but there are many other good ones.
What produced the neutrino background?
Sorry?
To show there is a background.
Yes.
Produced by what?
Well, yeah, this part here is from solar neutrinos. This part here is mainly from atmospheric neutrinos. There's also, interestingly, a component of diffuse supernova neutrinos that can be most relevant in this transition region between the two. That part we don't know very well, but the solar and the atmospheric we know very well. We know exactly where the red region is. In fact, this uses a process of coherent elastic scattering against nuclei. This was first measured experimentally last summer by the coherent experiment using reactor neutrinos. So we confirmed that they interact in this way. We know how many there are, and the experiments just have to get down to there. And if you look at these projections, we're going to start hitting this soon. Okay. So, unknown unknowns. I could sort of leave this blank since I don't know what I don't know. But let me just give a theoretical argument. Why are there unknown unknowns? This might sound like a meta question, but you could ask, why don't we already know everything? Well, in fact, quantum field theory has a deep property that unfortunately, particle physics has a deep property that obscures information from us at high energies. And this is the real reason why we want to go to high energies, so it's worth talking about for a moment. And it's a technical fact called the Decoupling Theorem, and it sort of describes this schematic. So here if we organize things by energy or equivalently mass, we have the standard model particles characterized by the mass scale of the Higgs. Now suppose we do an experiment at some energy. This could be like the LHC at 13 GeV. Now suppose there are heavy states that have a larger mass. Well, you could ask, how come we don't see these states giving an effect on our experiments? Unfortunately, the decoupling theorem tells us that any effect of these heavy states is parametrically suppressed by a finite power of the energies of your experiment over the mass of those states, and then therefore as their mass goes to infinity, their effect goes to 0. And there's really no way around that, so quantum field theory has this natural property that it obscures high energy heavy things from low energy experiments. So that's actually the technical reason why it's not just that we want to make bigger colliders, there's no other way sometimes to get up to see what is at higher masses, other than going to higher energies. So that's kind of one reason why there's unknown unknowns. Formally, the effects of these states decoupled, and therefore they could be there and we won't see them until we go there. So I'll give one example of a type of particle where we can really gain a lot of power in looking for it by going to higher energies. And that's, we can ask the question, are there more forces beyond the known forces of the standard model, electromagnetism, weak, nuclear, strong, nuclear? There could be a fourth type of force. It would have its own force carrier because of this correspondence between spin-1 particles and forces. We call this a Z prime boson because it's like a heavy cousin of the known Z boson of the standard model. You can produce it at colliders like the LHC from taking a quark from one proton, anti-quark from the other, and making it. It can decay to two leptons. So we can look for that. The problem is that there's a background in the standard model that I already talked about, this Dilepton production that I want to use to measure the energy dependence of couplings. So you want to tell that you're doing this, but you have this background of this. So how do you look for this? Well, you can use this invariant mass variable that I mentioned before. It has the nice property that for this event, if you make the Z prime, then the invariant mass of these two leptons is given by the mass of the Z prime. It just follows by applying energy momentum conservation to this process. So what you want to do in practice is look at this distribution, look for a bump. We call this a bump hunt. This is an example, recent example from the Atlas experiment. So here they're looking at events with an electron and a positron. They form the invariant mass. You get this falling distribution that shows the data. If there were a new force, this heavy Z prime, you would get a bump. So the red, green, blue show examples of a hypothetical new force carrier with a mass of 3, 4, 5 TeV that you don't see. So you can exclude the presence of there being a bump of that type with this data, and then it sets limits on the presence of new forces. And here you really need to kind of go to the energies where you have enough energy to make this particle to see this bump. And if you're at lower energies, you can't because of this decoupling theorem. So that shows the present status. Let me show you where we're going to go with this. So this shows the mass of this new force carrier, the Z prime. This is its coupling strength, using a variable related to the alpha couplings that I discussed earlier. So here, well, the gray region is excluded by other low energy constraints. The blue region is excluded by this recent Atlas measurement that came out this past summer. The blue lines show the region that you can probe by collecting more data at the LHC. So it could be that the event rate is small enough that with the current 3% you haven't made enough to see it, and then you can probe out to these blue lines by collecting more data. So there's a region of new force carriers that we wouldn't see now, that just by running the LHC for longer, we would be making and seeing. Well, the things get really fun if you imagine that we get this 100 TeV collider, because now you can start making Z primes whose effects would really be obscured by the decoupling theorem at the LHC. So here, the plot on the left is contained within this box of the plot on the right. So log scale here going into much higher masses, and then the purple curves show the region of these force carriers that you would be able to produce at 100 keV collider that is hopeless to see at the LHC because of this decoupling theorem. So that's just one example, but really the point, the big picture point is that by going to higher energy, you can make new particles whose effects are just parametrically too small to see at the energies that we're testing now. So that's just one example of an unknown unknown. Okay, so for the final part of the talk, I want to discuss the most subtle case, the unknown knowns, the ones that Rumsfeld forgot at first. Things we think we know, but we don't know. And we think we know how standard model processes will work. So if we're making a new particle, then we don't know what's happening. But we think we know the behavior of known particles like dileptons. So for this part of the talk, I want to show examples where there's new physics. We're not making new physics directly, maybe it's too heavy, but the new physics can still imprint on known physics in subtle ways, but ways we can still uncover. And it can change things that we thought we knew. And a useful language for talking about this is something we call effective field theory, which can describe the physics we're seeing experimentally. This is schematically how to think about effective field theory. If we might have we say that we have an ultraviolet theory that applies at all energies. An effective field theory is a theory we can construct that applies at lower energies, and it's simpler. So if you take this literally, it has less pixels. So the advantage of this is it's simpler, and you don't need to know the full image. You can construct this out of less degrees of freedom, and it can approximately describe what's happening at low energy. That's sort of the cartoon. Let's now apply this idea to the standard model. So we have the standard model particles. Suppose there's some heavy physics. And since the LHC hasn't seen any obvious deviation yet, it's likely that there is some gap before we see the new physics. Well, in this case, if we're not actually making the new particles, we can describe their effect using this effective field theory technology. We can form an effective theory where we have the standard model, and then we add new interactions of just standard model particles, but these new interactions are generated by the heavy physics. And the advantage of this approach is we don't actually have to know what heavy physics is. There's only a finite number of these interactions that can capture their effects, and then we can look for these interactions at low energies. So this approach has been kind of gaining momentum at the LHC, given that we haven't seen any obvious new physics. We should perhaps look carefully for more subtle effects of new physics in these interactions. So there's a few ways that they can be manifest. One nice example is you can have new interactions involving the Higgs boson. They can be generated if there's new heavy physics that interacts with the Higgs boson. It can change the apparent couplings to the Higgs boson that we're seeing. So I discussed before how the LHC and beyond can measure with increasingly better precision various Higgs couplings. There's well-defined predictions for these couplings in the standard model, but in this effective field theory where you have new interactions, then those standard predictions can be modified. So this shows each of these are different interactions that are beyond the standard model involving the Higgs that could be present, and here a larger scale and smaller effect, and then this shows the reach to look at these different interactions with various proposed future plus E minus colliders, where you can look for the effects of these interactions out to energy scales of 1 to even 100 TeV. So earlier I framed it as a known because the standard model makes a prediction for Higgs couplings, but in fact it's very motivated that new physics could change Higgs couplings, and by measuring it, we will either confirm the standard model or see evidence for these interactions, or if not, then we can constrain the size of these interactions. Okay, so that's one case. The other case I'll discuss is something that we call oblique parameters, and these are new interactions that can be present that involve forces. So we take standard model forces, so electromagnetism or the weak nuclear force, and suppose that these forces interact with new physics that is heavy. Then the effect of the new physics can be to change the behavior of the known forces at the energies we're testing them. We call this idea oblique parameters. There are 4 types of interactions that encapsulate the leading ways that new physics can change the forces at low energies that are given by these 4 pictures. And this is the utility of this effective field theory approach. In general, there's an infinite number of high energy, there's an infinite number of things that can appear in this box, but its effect can be captured by 4 types of interactions at low energies. So the rules of quantum field theory really restrict types of effects that are motivated to look for. And now we can ask, well, can we use the LHC or other experiments to test whether these extra interactions are present? Okay? So all four of these interactions affect the behavior of dileptons, this process we've been talking about. All four of the interactions affect the behavior in this peak region where you're making Z bosons. And in this region you can study best by making lots of Z bosons. In fact, the best way to do that is an E plus E minus collider making Zs. These two operators, W and Y, they change the shape of this tiny invariant mass scale, and the effects are quantum mechanical, and so you can have either constructive or destructive interference with the standard model processes, which is why there's two signs. You can either have extra events or less events than you expected in the standard model. So now we can look for both of these types of effects. So first I'll show you what we can do from this region, and then I'll show you what we can do from this region. Okay, so this shows what you can do mainly from studying the Z boson. Here, these are the two extra interactions that can be present. And here the axes are chosen such that the standard model lives at 0, 0. And then if these interactions are present, you move away from 0, 0. And what we currently know is that we live somewhere within the dashed line, and we mainly know that from actually colliders earlier than the LHC, like a collider called LEP at CERN that studied the Z boson with great precision, and it told us we live in this dashed region. And with the LHC, we're actually not going to improve things much. We're going to move from the dashed line to the solid blue line by running the LHC, the full LHC program. However, these inner circles show how well you could do with future E plus E minus colliders that would study the properties of the Z with greater precision than the older experiments. And the standard model is 0, 0, so you're kind of dramatically zooming in and constraining the size of these extra interactions if we have a future E plus E minus collider. Okay. The other case I mentioned is that we can look at this tail region. So in a little more detail, we can look at events with two leptons. They can be impacted by these new interactions. We can look at the invariant mass spectrum. Although now we're not going to get a bump like we had before with the Z prime, we'd have a more rapid change in shape. The other thing we can look for at the LHC is events with a lepton and a neutrino. So here, where you pull an up quark out of one proton, anti-down quark out of the other, and through a W boson, make a lepton and a neutrino. There's a technical difference here. For the case of the two leptons, you measure both of them, so you have all the kinematic information. Here, you don't measure the neutrino. You can use conservation of momentum to infer its momentum, but only in the plane transverse to the collision. So the way we have to deal with that is we can't actually form the full mass. We can form sort of a two spatial dimension cousin of the mass where we project everything into the transverse plane. We call that transverse mass. But anyway, bottom line is we have distribution of this variable. It's impacted by this new interaction, and we can look for its effect. Okay. So this shows what you can do. Presently, so the standard model is 0, 0, where we have these two interactions. All we know right now is that we live within this big gray bubble. But the LHC, after it collects the full data set, can show that we live within the green and purple bands. And before we did this study, it was actually believed that the LHC wasn't going to improve on oblique parameters beyond the old LEP constraints. So we were the first to show you could actually dramatically improve it by looking carefully at these high energy distributions. And if you want to more futuristically, if we were to have a higher energy collider, these effects become much bigger. So the whole plot on the right lives within the red box on the left, where its standard model is at 0, 0. So you can really zoom in and constrain the size of these extra interactions by studying the properties of leptons at 100 dB per proton. Okay, so an application of this idea would be something I mentioned earlier in the unknown part. You could have a new force carrier, the Z prime, that we can look for. And before I talked about looking for it directly by producing the Z prime, getting a bump in the dilepton invariant mass distribution. But from this effective field theory approach, you can actually still look for its effect at energies below its mass because it can generate this new interaction. So in the left case, you're really making the Z prime. On the right case, you're seeing its indirect effects. And it's been kind of well mapped out in the past what you can do if you directly make this. In this recent paper, we were the first to look at how well you could do by looking for its indirect effects. So that's summarized in this plot. Here you have the Z prime mass, its coupling strength. I showed a similar plot before where I only showed the blue lines. So the gray and the shaded areas are already excluded. The blue lines here show how well you can do ultimately with the rest of the LHC data by directly reducing the C prime. The red region is the new region we identified where you're not able to make it directly, it's too heavy. However, it generates these interactions that affect standard model processes, dileptons, that you can then look for by studying precisely dileptons at the LHC. We would have liked a very dramatic bump, given its absence. By precisely studying what we're collecting, we can look for subtler effects that we can still be sensitive to. And there's much more physics we can look for with this approach. It's an approach I think worthy of more exploration. Okay, so we're wrapping up. As I told you, I first forgot unknown knowns. He provisionally provided a definition in his 2004 memo, things you think you know, but it turns out you do not. So someone from the audience asked if that's really the right definition, which is an interesting question. There's a documentary that I recommend about Donald Rumsfeld by Errol Morris, who's not a fan of Rumsfeld, about his career in Iraq and things you know and don't know. And in the interview for this movie, he provides an alternate definition for unknown knowns. Where the documentary filmmaker reads back Rumsfeld's 04 definition to him, and he's like, I don't like that, and he suggests, how about this? Things that you possibly may know that you don't know you know. So it might sound like we're jumbling words, but actually, number one and number two are very different. Because here it's saying you know less than you think you do, here it's saying you know more than you think you do. I want to know more, so I like the second one much better. And applying that to particle physics, what I would say is we might know more than we think, in the sense that measurements we've already collected might have information that, when kind of properly studied, might reveal things that are not obvious with crude analysis. And the types of studies I was just showing are of that type, where it's not a very dramatic effect, but there can be subtle effects, where if you compare with precision theoretical predictions, you can reveal new physics. It's not dramatic, but still detectable. So I showed this whole collection of standard model measurements. Here I only really talked about three types, Higgs, lepton, and lepton neutrino. There are many others where people haven't even thought about this approach yet of asking what can we learn about new physics beyond the standard model using things we're measuring predicted in the standard model. And it could be that even with existing data, that we might actually know more in the sense that the data is on tape than we think we know. If we maybe just need to analyze it in the correct way or do more theoretical calculations with it. Okay, so to summarize, this talk was an application of the Rumsfeld matrix of knowledge. Probably useful in many fields. This one's a little more subtle, so there's two definitions. Anyway, we translated this to particle physics. So here's the Rumsfeld matrix of particle physics. And I showed a few examples of each, just as a case. There are many more. But a lot of what you can do can be classified into these four areas. So known knowns is the standard model. We have a theoretical description, but we can still test it in new regimes. An example I highlighted is the standard model predicts that the strength of forces depends on energy. This has been tested only for one of the three. And the LHC and beyond the LHC can test if the other forces also depend on energy, the way we predict. Okay, well, known unknowns, there are cases standard models known to be inadequate. The key one is dark matter. It doesn't describe dark matter. Hopefully direct detection will discover dark matter, but if it doesn't, the LHC can look for versions of dark matter that direct detection would be invisible to. Okay, unknown unknowns is surprises, but actually there's a good physics reason why there are still surprises. Heavy physics mathematically decouples from low energy physics. It's called the Decoupling Theorem. It's why we have to sometimes actually go to the higher energies to see its effects, and therefore we may be surprised. There's really no way of avoiding that. Okay, finally, unknown knowns is more subtle, but here I framed it as cases where new physics does not be directly produced, but leaves indirect effects on things we're measuring. It's subtler, it's harder, but it's less explored, and I think that there's a lot of potential in this box. Okay, thank you.
Yeah, concerning the new heavy state, can you learn anything on that from the Big Bang? Because you study all the energy.
It's a very good question, and indeed, cosmology is a completely independent probe. And in a sense, dark matter would be an example of that, because it could be a heavy state that was made in the early universe. The problem with that approach, though, is all we really know for sure is that the temperature of the universe was at least 1 MeV. It had to be hot enough for Big Bang nucleosynthesis when it operated like a nuclear reactor. But we we don't actually know how hot it was. We call that the reheat temperature, and it's an unknown parameter of cosmology that could have been as low as 1 MeV. In principle, the LHC may already be going to much higher energies than the universe ever probed thermally, or the universe may have been hot enough to make heavier things, so that's actually not known. But indeed, cosmology is if the universe was hot enough to make heavier states, then that's an independent way of testing them that's very interesting, and dark matter might be an example already of that.
Well, I think that the universe just started at 1 MeV would be very...
Well, you had some, the standard view is you had some period of inflation,
right,
and then you had to reheat the standard model. So the energy that was in the inflaton had to go into the thermal bath of the standard model, and then what temperature the standard model was heated to is an unknown. So the all we know experimentally is that it was at least 1 MeV for BBM.
Where would you put the dark matter question explained by not understanding the gravitational attraction? How would that be tested?
It's a very good question. Yeah. Well, I would say there's 3 different sort of scales where we understand dark matter. There's galactic rotation curves, the speed of stars, where modifying gravity could easily produce the same effects. But there's also cluster mergers like the bullet cluster and the cosmic microwave background. So the cold dark matter idea elegantly explains all 3 with the same model. The challenge for modifications of gravity would be to explain all 3 pieces of evidence. So one way to try to test ideas along those lines would be to see if we can explain the types of evidence on all 3 scales that cold dark matter can explain already.
You stated that the biggest problem is the decoupling theorem, and then you said that you can look at new interactions to overcome this problem. But how do new interactions at still lower energies can fix the problem of the decoupling theorem?
Yeah, very good question. And indeed, so I was not overcoming it, I was living with it. So if we look, so the decoupling theorem tells you get this function, energy over mass to the n. And in the case of new interactions, the size of those interactions is given by this formula. So really, it's just you can overcome it by performing precise measurements where you can still deal with the E over m suppression. And then as m gets too big, then the ability to do that goes away.
But the m parameter is it's constructed not by the energies there. If you add more interactions to the standard model, the m won't get smaller.
No, m is just m is fixed. It's the mass of whatever heavy states are there, and then their effect at low energy is given by this expression. And when new interactions capture the effect, the size of the effect of those new interactions is given by this expression.
And by adding new interactions, you modify m in such a way.
No, m is staying the same. New interactions are just capturing this effect that's dictated by this expression. So m is constant. That's whatever.
So how the new interactions at the lower energies will give you some information about the higher energies that you can't overcome.
Well, maybe if I do concrete. Okay, so like here, for example, there's some new m is up here, and we can still see its effect over here, the size of this change. So you want to see that it's red versus blue, and the fractional size of this change is going to be given by this E over m factor. The nice thing about this particular process is we have a percent level, both theoretical and experimental understanding. So by doing percent level measurements, we can see E over m's as small as 1%.
Okay, let's thank Josh again.